In 1997, there was this paper published by two mathematicians that, honestly, it kind of terrified the whole artificial intelligence community.
Oh, absolutely. It sent shockwaves. Because they proved, mathematically, without any room for debate, something completely counterintuitive.
Right. They proved that if you build a machine with a perfectly open mind, like a learning algorithm that makes absolutely zero assumptions about the world.
It is mathematically guaranteed to learn absolutely nothing.
Which is wild. I mean, we spend so much time culturally, trying to eliminate bias.
Yeah, we treat bias as the ultimate enemy. But statistically, if an algorithm has no bias whatsoever, it's paralyzed.
It just stares at the data, right?
Exactly. It looks at a data set and has no logical reason to pick one conclusion over, say, an infinite number of other completely absurd conclusions.
And that profound paradox is exactly what we are exploring today. So welcome to this custom deep dive. We have a massive mission for you today.
We really do. We're tackling a formidable stack of sources today.
Yeah, we've got some heavy hitters. Christopher Bishop's pattern recognition and machine learning, Tom Mitchell's classic text machine learning, and Shelev Schwartz's understanding machine learning.
Foundational texts, the real bedrock of the field.
And we are going to use them to decode statistical learning theory. We're going to look at the actual mathematical architecture of how machines, and honestly, arguably, how we learn from experience.
Right. We're going to unpack the mechanical reality behind all those buzzwords that get thrown around in the AI hype cycle.
Like learning and generalization.
And bias, exactly. But we're going to look at what those words actually mean when you force them into an equation.
Because when you strip away the marketing and the sci-fi tropes, what you're left with is a series of fundamental, almost epistemological questions.
Yeah, like how do we trust that a pattern we observed in the past will actually hold true tomorrow?
Okay, let's unpack this. We have to start by defining our terms, I think.
Definitely. You can't do the math without defining the terms.
Right. So if we're talking about machine learning, we need a really rigorous definition of learning itself. Because early on, computer scientists were just obsessed with trying to emulate human biology, right?
Oh, yeah, they were all trying to build digital brains. It was very messy and philosophical.
But Tom Mitchell's text shifts that paradigm entirely. He gives this formal definition that says learning is just a combination of three things: a task, which he calls T, a performance measure, P, and source experience, E.
And by framing it that way, Mitchell takes learning out of the realm of, philosophical mystery and turns it into a highly specific optimization problem.
Right, it's just a math problem now.
Exactly. He stated that a computer program learns from experience E with respect to some class of tasks T and performance measure P if its performance at those tasks improves with experience.
Okay, let's ground that for everyone listening. Let's say you want to build an algorithm to play checkers.
Classic example.
The task, T, is simply playing the game of checkers. And the experience, E, is having the algorithm play, I don't know, tens of thousands of games against itself.
Right. It's generating its own history to learn from.
But the crucial part, the part that really dictates everything the machine is going to do, is P, the performance measure. P is just the win rate.
And what's fascinating here is how ruthless that P variable is. I mean, it is completely unforgiving.
It really doesn't care about anything else.
Not at all. The machine doesn't care about the beauty of a checkers move. It doesn't understand the psychological pressure of the game or the joy of winning.
It's just a mathematical engine relentlessly trying to push the value of P higher.
Exactly. If P goes up, it learned. If P goes down, it failed. End of story.
But wait. If learning is just ruthlessly optimizing a metric based on a historical data set, what stops the machine from optimizing well too well?
Now you're hitting the core issue.
Because I can totally imagine a scenario where the algorithm memorizes every single board state it encountered in its practice games, like to the point where it plays perfectly against itself.
Right, it achieves a perfect score on its past experience.
But then, the second a human opponent makes a weird, novel move that wasn't in the training data, the machine just crashes and burns.
You've just identified the central crisis of the entire field. It is the fundamental tension between the ultimate goal, which is generalization, and the ultimate trap, which is overfitting.
Generalization being the goal.
Yes. Generalization is the ability of a model to correctly categorize entirely new examples, things that differ from what it saw in training.
Because the machine has to operate in the real world. I mean, a self-driving car algorithm can't just be good at driving on the specific roads it practiced on.
Exactly. The training data is just a proxy for reality. It's a tiny sample. If a model only memorizes that sample, it is utterly useless to us.
And Christopher Bishop illustrates this mechanic so brilliantly in his book with that scenario called polynomial curve fitting.
Oh, the sine wave example. It's a classic for a reason.
Yeah, he sets up this synthetic problem. He generates a perfect, smooth sine wave, just a wavy line oscillating up and down. And that wave represents the ground truth of the universe.
But in the real world, we never get to see the perfect ground truth, do we? Our data is always messy.
Always. So Bishop takes 10 random points along that perfect sine wave, but he intentionally corrupts them.
He adds random Gaussian noise to each point, right?
Exactly. So now you don't have a perfect wave anymore. You just have 10 dots scattered roughly in a wavy pattern, but they're sitting slightly above or below where the true wave actually is.
Because of the noise.
Right. And the learning task is to feed those 10 noisy dots into an algorithm and ask it to magically recreate the hidden wave.
And the algorithm tries to do this by drawing a polynomial line through that space.
And we can actually control how flexible this line is, right? By changing the order of the polynomial, which Bishop represents with the letter m.
Correct. So let's say we set m equal to 1.
We're basically telling the algorithm, you are only allowed to use a rigid straight diagonal line.
Which is a textbook case of underfitting.
Yeah, because a rigid straight line cannot capture the oscillation of a sine wave.
Yeah.
It's impossible.
No matter how you angle it, a straight line will completely miss the true pattern. Its performance on the 10 dots is terrible, and its performance on any future dots will also be terrible.
So naturally, we say, okay, let's give the algorithm a more flexible tool. We bump the complexity up. We set m equal to 3, the third-order polynomial.
Meaning it can curve?
Right. And this turns out to be the sweet spot, doesn't it?
It really is. The m equals 3 curve swoops up and down, and it captures the general essence of the sine wave.
But it doesn't hit every single dot perfectly.
No, it doesn't, and that's actually a good thing. It ignores the random noise, but it finds the underlying signal. It generalizes.
But human nature, and honestly, algorithmic optimization, always wants a perfect score.
We can't help ourselves.
Right. If the algorithm is judged solely on its performance measure, p, and p is minimize the distance between the line and the 10 training dots, the machine is going to demand more flexibility.
So Bishop cranks the dial all the way up to m equals 9, a ninth-order polynomial.
And keep in mind, we only have 10 data points to begin with.
Right, and an m equals 9 polynomial has 10 parameters. That's 10 independent dials it can turn to adjust the shape of its curve.
If you look at the graph of this in Bishop's text, it is genuinely horrifying.
It's a mess.
The m equals 9 curve perfectly, flawlessly intersects the dead center of every single one of the 10 training dots.
The error on the training data is absolute 0. Mathematically, it achieved perfect performance on its past experience.
But between those 10 dots,
Mhm.
the curve rockets up to positive infinity and plunges down into negative infinity.
It oscillates violently.
Yeah, if you ask this m equals 9 model to predict a new data point that sits just a fraction of an inch to the left of a training dot, the prediction would be astronomically wrong,
And this is the mechanical definition of overfitting.
just totally losing the plot to memorize the data.
Exactly. To force a curve to hit 10 noisy dots perfectly, the internal parameters, the actual mathematical weights of the algorithm, they have to explode in size.
What do you mean by explode?
Like, one weight might be positive 1,000,000 and the adjacent weight might be negative 1,000,000, just to pull the curve into this violent hairpin turn to hit an anomalous data point.
Oh, wow.
Yeah, the model has completely abandoned the true signal because it's obsessively memorizing the noise.
But wait, if the rule we gave the machine was simply minimize the error on the training data, and the m equals 9 model followed that rule perfectly by driving the error to 0,
Yeah.
doesn't that imply the mathematical rule itself is fundamentally flawed?
It implies that the rule is incomplete. The rule you're referring to is empirical risk minimization, or ERM.
DRM.
ERM basically states that a learning algorithm should choose the hypothesis that minimizes the average loss on the empirical training data.
Which, I mean, sounds incredibly logical. Why wouldn't you pick the model that makes the fewest mistakes on the data you actually have?
Because the data you have is not reality. It is a noisy, limited sample of reality.
Right.
If ERM is your only guiding principle, you are mathematically guaranteed to overfit the moment your model possesses enough capacity to memorize the noise.
It's just a matter of time.
Exactly. And ERM's failure leads us directly to the foundational tension in all of statistical learning theory, the bias-variance trade-off.
Okay, I really want to break this down without the textbook jargon.
Yeah.
Because I'm struggling to see how adding complexity physically changes these two types of error.
Sure, let's do it.
Let's start with bias. And just to be clear, in statistics, this doesn't mean prejudice, right?
No, not at all. Statistical bias refers to the error introduced when you approximate an incredibly complex real-world problem with a much simpler model.
Okay, so think of our m equals one straight line.
Right, that line has extremely high bias. Why? Because it approaches the data with a rigid preconceived assumption. The universe is a straight line.
It's stubborn.
Exactly. It doesn't matter what the data actually says, the model stubbornly refuses to curve.
So a high bias model is basically just a stubborn model. It ignores the nuance of the data because its internal structure is just too simplistic.
That's a great way to put it. And then on the other end, you have variance.
Okay, what's heard of us?
Variance measures how much the model's prediction would change if you trained it on a different set of data from the exact same universe.
Let's apply that to the m equals 9 model, the wildly oscillating curve.
The m equals 9 model has incredibly high variance. Imagine we go back to the perfect sine wave, but this time we draw a completely different set of 10 noisy dots.
Right.
And we train a new m equals 9 model. Because it is desperately trying to hit every single new dot perfectly, the new curve will look radically, entirely different from the first curve.
Oh, I see. Because the noise is in different places now.
Exactly. Its shape is hypersensitive to the specific sample of training data.
Okay, I get it now. So if bias is being too rigid to adapt, variance is being so hyperreactive that you completely change your identity based on whoever is in the room with you.
That is a perfect analogy, yes.
But if ERM naturally pushes algorithms toward high variance by trying to hit every point perfectly, how do we physically stop the machine from being so gullible?
We have to artificially intervene in the ERM equation. We have to introduce a mechanism that physically restrains those massive parameter weights from exploding like we talked about earlier.
And what is that intervention called?
We call this regularization.
Regularization. Okay, I'm struggling to see how adding a mathematical penalty actually shrinks a variable. Can we ground this? How does the code actually execute that constraint?
Let's try to visualize the math. In pure ERM, your algorithm is basically searching a landscape of possible parameters, trying to find the lowest valley, which represents the lowest error.
Okay, I'm picturing a landscape.
But with regularization, we add a literal penalty term to the loss function. We say to the algorithm, find the lowest error, but we are going to add an artificial cost based on how large your mathematical weights are.
So the algorithm is trying to minimize a total score now, and the total score is error on data plus size of the weights.
Exactly. The two most famous techniques for this are L2 and L1 regularization, which Hastie and Tibshirani discuss heavily in their texts.
Let's start with the L2. I think that's also known as ridge regression.
Correct. L2 calculates the penalty by squaring the magnitude of all the parameters.
Okay, squaring them. What does that do?
Geometrically, it restricts the algorithm to searching for solutions within a rigid circle centered around 0.
So even if the absolute lowest error on the training data is way outside that circle, the algorithm isn't allowed to go there.
Right. It has to settle for a slightly higher error on the training data just to ensure its parameters stay small and contained within that circle.
And by keeping the parameters small, you prevent the curve from violently oscillating.
Exactly. You force it to be smooth. You artificially increase the bias slightly to massively decrease the variance.
Okay, here's where it gets really interesting to me. That's L2, which shrinks everything proportionally.
Right.
But the texts also talk about L1 regularization, called lasso. And lasso does something wildly different, doesn't it? It doesn't just shrink variables, it entirely deletes them.
It does.
How does the math do that?
It comes down to the geometry of the penalty. While L2 squares the parameters, creating a circle, L1 takes the absolute value of the parameters.
And geometrically, what is the absolute value?
In a geometric space, a constraint based on absolute values doesn't form a circle, it forms a diamond, with sharp pointed corners sitting directly on the axis of the graph.
Okay, I have a mental image of a diamond on a graph.
Good. Now, as the optimization algorithm expands its search outward from the ERM minimum, looking for a solution that fits inside the allowed boundary.
Yeah.
It is overwhelmingly likely to intersect the diamond constraint exactly at one of those sharp, pointy corners.
And because those corners sit exactly on an axis, the coordinate for the other variable is absolute 0.
Yes. You nailed it. L1 forces the parameter of the less important variable to become exactly 0. It actively deletes irrelevant features.
That's amazing.
This property is called sparsity. For example, if you are predicting housing prices and you feed an L1 model 1,000 variables.
Including, like, the square footage of the house and the color of the owner's shoelaces.
Exactly. L1 will drive the mathematical weight for the shoelaces to absolute 0. It just drops it.
It's performing built-in variable selection.
It is. And the texts also mention elastic net, which is just a mathematical hybrid of both, utilizing the sparsity of the L1 diamond and the stability of the L2 circle.
But I got to say, everything we are talking about right now feels like engineering tricks.
Yeah.
Like we're just hacking the loss function to keep the math from exploding.
It is engineering, I'll give you that. But
Huh.
Vapnik and Shalev-Schwartz elevate this from a neat trick into a sweeping theoretical framework.
And what's that called?
Structural risk minimization, or SRM.
Okay, what is this shift from empirical risk minimization to structural risk minimization?
Well, ERM operates on a flat plane. It just searches one massive space of functions. SRM introduces a hierarchy.
A hierarchy of what?
It pre-structures the hypothesis space into nested subsets of increasing complexity. It demands that the algorithm first search the absolute simplest subset,
Okay.
and only if the error is unacceptably high is the algorithm allowed to graduate into searching a slightly more complex subset.
So you are structurally forcing the model to exhaust all simple explanations before you allow it to use a complex one.
That's it exactly.
Well, wait, hold on. Isn't that literally just Occam's razor? Like the philosophical idea that the simplest explanation is the best.
It is.
Why should a computer care about a human philosophical razor?
That is a brilliant question, and the answer bridges computer science and information theory. Why should a computer care? Because of a concept called minimum description length, or MDL.
MDL.
Occam's razor isn't just human aesthetics. It is a mathematical reality about data compression.
Okay. How does compression relate to learning?
Think about what learning actually is. If you truly understand a pattern, you can describe it using very few words.
Give me an example.
If I give you the sequence 2, 4, 6, 8, 10, 12, you don't need to memorize the numbers. You just say even numbers.
Oh, wow. I compress the data using a rule.
Exactly.
I love this analogy. It's almost like packing for a trip. You have to fit all the data, your clothes, into a suitcase.
Yes. To take your suitcase analogy further, MDL states that the best model is the one that minimizes the total description length.
Which would be what in this analogy?
The total description length has two parts. The size of the suitcase itself, which is the complexity of the model, plus the list of things that didn't fit in the suitcase and had to be shipped separately, which are the errors the model made.
Oh, this makes so much sense. If you use an m equals 1 straight line, your suitcase is incredibly tiny, but you leave a massive amount of clothes behind, so your error list is huge. Total description length is bad.
Right. And if you use the m equals 9 curve, your error list is 0, you packed everything. But the mathematical equation for that curve is so massively complex, the suitcase is the size of a cargo ship.
So total description length is also bad.
Exactly. MDL proves mathematically that the optimal model is the one that perfectly balances the size of the rule with the size of the exceptions.
Okay, so we've established the rules of regularization and SRM. But if I am a data scientist deploying a model in the real world today, how do I know it won't just explode tomorrow? Is there an actual theoretical guarantee that any of this works?
That brings us to one of the most elegant theoretical breakthroughs in the field. Leslie Valiant's 1984 paper.
What did he introduce?
He introduced the PAC learning framework. PAC stands for probably approximately correct.
I love the mathematical humility of that name. Probably approximately correct. It just feels very grounded.
It really is. Prior to Valiant, theorists were obsessed with finding algorithms that could identify concepts with absolute 100% certainty.
Which is impossible.
Right. Valiant looked at the noise in real-world data and realized that demanding absolute certainty is mathematically impossible. You cannot definitively prove that the sun will rise tomorrow based solely on past observations.
So he shifted the goalposts.
He did. He said, let's stop demanding perfection and let's start calculating the exact boundaries of our imperfection.
And how did he measure that?
He defined two specific parameters. Epsilon, which represents the error margin. This is the approximately correct part. You demand that the model's error is less than epsilon.
Okay, and the second parameter?
Delta, which represents the confidence level. This is the probably part. You demand a probability of 1 minus delta that your model will actually achieve that epsilon error rate.
So practically speaking, I can go to my boss and say, I am 99% confident that's delta, that this model will be at least 95% accurate, which is epsilon.
Exactly. And the Pake's framework fundamentally asks, to guarantee those specific epsilon and delta bounds, how much data do you need?
And that's what they call sample complexity, right?
Yes. And once you have that data, how much computing power will it take to process it? That is computational complexity.
But wait, if I demand like 99.9% certainty with a 99.99% accuracy rate, what happens to the data requirement?
It scales exponentially. You'd need a staggering amount of data. But here is the critical part. The amount of data you need isn't just driven by epsilon and delta.
What else drives it?
It is heavily driven by how complex your model is. A simple straight line needs very little data to prove it's probably approximately correct. A massive neural network needs an absolute ocean of data.
But earlier, when we looked at the m=9 polynomial, we saw that just counting the number of parameters is a flawed way to measure complexity, right?
It's very flawed.
Because a model with 10 parameters can behave wildly differently than another model with 10 parameters.
Exactly.
So we can't just count the variables. How on earth do we measure a model's imagination to calculate the backbones?
This introduces a concept developed by Vladimir Vapnik and Alexei Chervonenkis.
The VC dimension.
Yes, arguably the most important metric in statistical learning theory. The VC dimension doesn't count parameters at all. It measures the sheer geometric flexibility of a model.
How does it do that?
It measures a model's capacity by calculating the maximum number of data points the model can shatter.
Shatter. Okay, that sounds like a violent physics term, not a statistical one. Let's visualize this. What does it mean to shatter data?
Imagine a flat green field. And in this field, we have a flock of animals. Some are sheep, some are wolves.
Okay, sheep and wolves.
Your learning model is a simple, straight wooden fence. Your task is to build a single straight fence that perfectly separates all the sheep on one side from all the wolves on the other side.
Okay, I have my straight fence and I have my field.
If I place 3 animals in the field, arranged in a triangle, no matter which of those 3 animals are sheep and which are wolves, can you always build a single straight fence to separate them?
Let me think. If it's 2 sheep and 1 wolf, I just draw a line slicing the 1 wolf off. If it's 3 sheep and 0 wolves, I just draw a line totally outside the triangle.
So, yes.
No matter what biological configuration you give me, I can angle a straight fence to separate the 3 animals perfectly.
Precisely. Because your straight fence can adapt to every possible combination of those 3 points, we say the straight line can shatter a set of 3 points.
Okay, I'm with you.
But now, let's escalate. I place 4 animals in the field, and I arrange them in a perfect square.
4 animals, square formation.
I make the top left animal a sheep, the bottom right animal a sheep,
Okay.
the top right animal a wolf, and the bottom left animal a wolf.
Wait, so the sheep are diagonal from each other and the wolves are diagonal from each other?
Exactly. Can you build a single straight wooden fence that separates the sheep from the wolves?
No. If I draw a line vertically down the middle, I get 1 sheep and 1 wolf on each side.
All right.
If I go horizontally, same thing. If I try to go diagonally, the fence just crashes directly into the animal.
It does.
To separate a diagonal configuration, I would need a curved fence, or like 2 separate fences. I cannot do it with 1 straight line.
And this is the famous XOR problem. Because there is at least 1 configuration of 4 points that your straight line cannot separate, your model fails to shatter 4 points.
Wow.
Therefore, the VC dimension of a 2-dimensional straight line is exactly 3.
That is mind-blowing. It's just a pure geometric measurement of expressive power.
It is beautiful math, and this ties directly back to PAC learning and ERM. If a model's VC dimension is higher than the number of data points you have, ERM is completely useless.
Wait, why is it useless?
Because if a model can shatter your entire data set, it means the model is flexible enough to perfectly separate the data no matter how the labels are assigned.
Meaning it can memorize pure random noise.
Exactly. It guarantees overfitting. To have any confidence in generalization, your sample size must be significantly larger than the VC dimension of your model.
So infinite VC dimension means an infinite data requirement. We are constantly searching for ways to constrain the model.
Yes, always.
But how do we actually select the parameters when the data itself might be deceiving us?
When we are tuning the dials of our model, we generally rely on probabilistic estimation. The foundational approach to this is MLE, maximum likelihood estimation.
Which is a frequentist approach, if I remember my stats classes.
Yes, it is. MLE determines the parameters by finding the specific mathematical values that make the training data you observed the most probable outcome. It looks strictly at the data on the table.
But wait, if MLE just blindly maximizes the likelihood of the observed data, wouldn't a casino looking at a roulette wheel that lands on black 10 times in a row just assume the wheel is permanently rigged to hit black?
That's a great example.
Because that conclusion maximizes the likelihood of the 10 blacks.
Hmm.
How does the math prevent the machine from being that gullible to a small sample size?
It doesn't. That is the exact vulnerability of MLE. If your sample size is small, MLE will drastically overfit to the anomalies.
So how do we fix it?
To fix this, we introduce the Bayesian alternative,
What?
MAP, or maximum a posteriori estimation.
Okay, MAP.
MAP fundamentally alters the math by introducing a prior distribution.
Bayes' theorem. So we are combining what we see with what we already believe.
Exactly. Let's go back to your casino example. You watch the wheel hit black 10 times. That is the empirical data.
Right.
But your prior knowledge is that casinos are highly regulated, physics is reliable, and roulette wheels are generally 50-50.
So how does MAP use that?
MAT mathematically multiplies the likelihood of the data by the probability of the prior.
So the math is forced to weigh the 10 blacks against a massive pre-existing mathematical anchor that says this wheel is fair.
And because of that anchor, the algorithm concludes that the wheel is probably still fair and the 10 blacks were just a statistical fluke. It flat out refuses to overfit to the small sample.
That makes total sense.
And here's one of the most beautiful connections in all of statistical learning theory. MAP estimation and regularization are mathematically the exact same thing.
Wait, what? A Bayesian prior is the same as an L2 penalty.
It is. If you set up an MAP estimation and you declare that your prior belief is that the parameters of your model should be distributed normally around 0.
Like a Gaussian prior?
Yes. And you take the negative logarithm of that equation to solve it. The math simplifies down perfectly and exactly to ridge regression, the L2 penalty.
That is incredible. So when we add an L2 penalty to keep the weight small, we are implicitly acting as Bayesians. We are injecting a prior belief that the universe favors small, stable parameters.
Exactly. It is two different philosophical paths arriving at the exact same mathematical formula. And this is how we ensure statistical consistency and stability.
Let's define those terms quickly because the texts emphasize them heavily: consistency and stability.
Sure. Consistency means that as your sample size grows toward infinity, the error of your algorithm will converge to the best possible theoretical performance.
It's the mathematical guarantee that more data eventually overcomes a bad prior.
Right. Stability, on the other hand, measures sensitivity. If you have 1,000,000 data points and you change the value of just one single point, how much does the final curve change?
If the curve whips around wildly because of one point, it's unstable. It has high variance.
Exactly. Regularization and MAP priors are what guarantee algorithmic stability. We also evaluate this using model selection tools like AIC, the Akaike Information Criterion, and BIC, the Bayesian Information Criterion.
How do those work?
They are basically formulas that calculate a score for your model. They reward the log likelihood, how well it fits the data, but strictly subtract points based on the number of parameters.
So what does this all mean? We've talked about L1 and L2 penalties shrinking parameters. We've talked about structural risk minimization, restricting the hypothesis space, MAP injecting Bayesian prior beliefs, and AIC explicitly penalizing complexity.
It's a lot of techniques.
It is, but it seems like the overwhelming central theme of all of statistical learning is that we are constantly artificially injecting human assumptions into the math to keep it stable.
That is exactly what we are doing. Pure, unguided empirical learning, just staring at data without assumptions, fails. It always fails.
But this leads to a massive question.
Yeah.
If we are always injecting biases and assumptions to make these algorithms work, is it theoretically possible to build a master algorithm?
A master algorithm.
Yeah, an ultimate AI that makes absolutely no assumptions, has a perfectly open mind, and can universally learn any pattern purely from the data.
This brings us right back to the hook you opened the show with, the paper from 1997 by David Wolpert and William McCready.
The no free lunch theorem.
Yes. And the theorem proves that the answer to your question is a definitive mathematical no.
Break down the proof for me. How can they actually prove that a universal learner is impossible?
The no free lunch theorem evaluates learning algorithms across every possible data distribution in the universe.
Okay.
If you take any algorithm, from a simple linear regression to a billion-parameter deep neural network, and you average its performance across all conceivable problems, every single algorithm performs exactly the same.
Wait, so across all possible universes of data, A massive, state-of-the-art neural network is no better at predicting the truth than just flipping a coin.
Exactly. Because if you assume nothing about the underlying rules of the universe, every new data point is a completely independent, isolated event.
I'm not sure I follow.
Well, if a model sees a dot at x equals 1 and a dot at x equals 3, and it has no assumptions, it has no mathematical justification for drawing a smooth line between them. The dot at x equals 2 could be anything. It could be infinity.
Oh, wow.
Without an assumption like the universe favors smoothness, learning is strictly impossible.
So if you're a data scientist trying to choose between like a random forest or a support vector machine today, this theorem is why your boss is fundamentally wrong when they ask for a one-size-fits-all algorithm.
Precisely. To learn anything, an algorithm must possess what we call inductive bias.
Inductive bias?
It must be mathematically prejudiced. We must restrict its hypothesis space. We must program it to assume that Occam's razor is true, or that L2 parameters should be small, or that the VC dimension must be constrained.
It fundamentally flips how we view the word bias. I mean, in our social structures, bias is a failure of logic.
Right, it's a flaw.
But in statistical learning, bias is the literal prerequisite for intelligence. A perfectly open mind is a paralyzed mind.
Inductive bias is the engine of generalization. Without it, you are just memorizing isolated noise.
This has been a spectacularly dense journey. We started with Tom Mitchell, defining learning not as a mystical process, but as an optimization of a performance measure based on experience.
And we saw how optimizing perfectly for past experience leads to the violent trap of overfitting, visually proven by the exploding weights in Bishop's m equals 9 polynomial.
We recognized that empirical risk minimization is flawed, which plunged us into the bias variance trade-off, and we explored how to escape it using regularization.
The geometric circle of L2 RID regression, and the sharp variable deleting corners of the L1 lasso diamond.
We connected Occam's razor to the structural realities of minimum description length and data compression with that suitcase analogy.
We quantified the expressive power of a model using VC dimension, shattering our field of sheep and wolves to understand exactly how much data is demanded by the Pacquiao-learning framework to guarantee our models are probably approximately correct.
We explored how Bayesian priors in MAP estimation stabilize our math exactly the way regularization does.
And we finally collided with the no-free lunch theorem, accepting that mathematical bias is the only way a machine can learn anything about reality.
It's just incredible.
If I can leave you with one final thought to mull over.
Please do.
The math proves that an artificial intelligence cannot learn without massive prior assumptions. But look at human evolution. We marvel at the fact that a human toddler is an incredible few-shot learner.
Right. A child only needs to see two cats to perfectly generalize the concept of cat.
Exactly, while a neural network requires a dataset of 100,000 labeled images.
So why is the toddler so efficient?
Because millions of years of evolution have preloaded our human DNA with massive, intricate, inductive biases. We are born with built-in physics engines, with dedicated neural hardware for facial recognition, with instincts about object permanence.
We are the furthest thing from a blank slate.
Exactly. The ultimate artificial intelligence of the future won't be a perfectly open mind that learns everything from scratch. It will be an entity whose mathematical biases are perfectly, exquisitely tuned to the specific realities of the human world it aims to serve.
Wow.
So the question to leave you with is this. What inductive biases are you bringing to your own learning? Are your assumptions helping you generalize the signal, or are they causing you to violently overfit to the noise in your own life?
A profound question to end on. Thank you so much for taking this deep dive with us today. Keep questioning the algorithms, keep exploring the math beneath the surface, and we'll catch you on the next one.